Hello, Professor. My name is SIQI, metric number 2411986 from the Master of Business Analytics program at University of Malaysia, supervised by Professor T. Ramaya. Today, I will present my study titled Empirical Evaluation of Statistical and Machine Learning Models for Retail Supply Chain Demand Prediction, using Walmart's weekly sales data from 2010 to 2012 under a two-level forecasting framework. Demand forecasting accuracy is critical in retail supply chains for three main reasons. First, accurate forecasting helps optimize inventory, reducing stockouts and overstock, which is in turn lowers holding and markdown costs. Second, better forecasts improve customer experience, especially during peak and holiday periods, by maintaining higher service levels. Third, reliable prediction supports operational and strategic planning, including staffing, replenishment, and promotion planning, particularly for store-level decision-making. These motivations lead directly to the research questions of this study. This study has three main objectives. First, to compare forecasting performance between statistical models and machine learning models using MAE, RMSE, and MAPE. Second, to evaluate model performance across different aggregation levels, specifically aggregate level versus store level demand forecasting. Third, to derive managerial insights by identifying key demand drivers and translating model results into actionable recommendations. The study uses the Walmart weekly sales dataset obtained from Kaggle. The data spans 130 weeks, from February 2010 to October 2012, covering 45 Walmart stores across multiple regions. Key variables include weekly sales as a target variable, store identifiers, data as a time index, temperature, fuel price, CPI, and unemployment as micro macroeconomic indicators, and the holiday flag, a binary indicator for designate holiday weeks. From exploratory data analysis, three key patterns emerge. First, clear annual seasonality is observed, with recurring sales peaks around major holidays such as Christmas and Thanksgiving. Second, there is a significant store-level heterogeneity, with substantial variation in sales magnitude and volatility across stores. Third, holiday effects are pronounced, with visible sales spikes and higher volatility during holiday weeks. These findings suggest that different modeling strategies may be required at different levels of aggregation. This study adopts an end-to-end forecasting framework applied at both aggregate and store levels. For future engineering, like the sales variables, rolling averages, and calendar-based features are created to capture seasonality and persistence. For the training strategy, a time-ordered train test split with rolling origins evaluation is used to preserve temporal order and prevent data leakage. Model performance is evaluated using MAE, RMSE, and MAPE. This slide presents aggregate level forecasting performance using statistical models only. At the aggregate level, ETS achieves the lowest forecasting error, indicating strong capability in capturing overall seasonal demand patterns. ARIMA and seasonal naive provide reasonable benchmark performance, while Sarimax exhibits the highest forecasting error in this experiment. These results suggest that simpler statistical models are more effective for aggregate-level retail demand forecasting. The picture changes at the store level. Traditional statistical models exhibit limited performance under high variability as they struggle to capture store-specific demand patterns. In contrast, machine learning models demonstrate greater adaptability and robustness under heterogeneous store-level demand conditions. Specifically, XGBoost achieves the best overall predictive accuracy, delivering the lowest MAE and RMSE across most stores, while random forest shows strong robustness and stability, performing consistent well across the heterogeneous stores. This slide summarizes diagnostic insights and feature important findings from store-level machine learning models. From residual diagnostics, residuals are more centered around zero and relatively symmetric, indicating reduced systematic bias. However, tails and outliers remain, which is consistent with extreme weeks such as holiday periods. In terms of feature importance, lagged sales variables, especially lag 52, dominate predictive power, highlighting strong annual seasonality and demand persistence. Rolling mean features capture short-term trends, while macroeconomic indicators and holiday flags show relatively low importance in the global ranking, suggesting limited incremental predictive power beyond historical sales patterns in this model setting. To conclude, this study supports a two-level forecasting framework. At the aggregate level, classical time series models, particularly ETS, provide stable and interpretable forecasts suitable for high-level planning. At the store level, machine learning models, especially XGBoost and random forest, better catchable heterogeneity and nonlinear demand patterns, improving predictive accuracy. From a managerial perspective, aggregate forecasts can be used for capacity planning and budget allocation. Store-level machine learning forecasts support localized inventory and promotion decisions, especially around holiday weeks. And stores with high forecast errors can be monitored to identify local operational issues. Future research may incorporate explicit holiday calendars, hierarchical reconciliation forecasting, and rolling origin evaluation across different forecast horizons. Overall, the key contribution of this study is the empirical validation of two-level forecasting framework using real-world Walmart sales data. Thank you.